In this video, we'll continue in the 2.1 frequency distributions for organizing and summarizing data notes on page 3 and do the practice problems. For the following frequency distribution, identify the class boundaries, class midpoints, and then create a relative frequency chart and a cumulative frequency chart for the data. Circle all the lower class limits, underline all the upper class limits. We'll start there. We have trunk circumferences of 40-year-old apple trees, and our classes are the circumferences. So we are asked to circle the lower class limits. That is the first number in each class. 69, 80, 91, 102, 113, 124, and 135. And we're asked to underline the upper class limits. 79, 90, 101, 112, 123, 134, and 145. We're also asked to find a number of different characteristics of this frequency distribution. You can see that I'm circling the actual frequency distribution. It's just this first two columns, circumference and frequency. But we're asked to find the boundaries, midpoints, relative frequency, and cumulative frequency. I'd also like to find the class width. So I'm going to write that above and we'll start there. So to find the class width, what you do is you take two consecutive lower class bounds and subtract them. So 80 minus 69 gives us 11. So the class width is 11. So that means if I take and add 11 between any two lower classes, I'll get from one to the next. So 11 is the lower, or is the class width. That also works. You could add 11 to this bound of 79, and that's how you get 90. 90 plus 11 is 101. 101 plus 11 is 112. So that is our class width. Now we need to find the boundaries. As a reminder, all of these terms are defined on the first page of your notes for this section. But in order to find the boundaries, what we're going to do is we're going to take an upper class limit and the next lower class limit, and we're going to average them. So here we'll have 79 plus 80 over 2. Well, that's going to give me 79.5. So the boundary between these two classes is 79.5. So that acts as an upper boundary of this first class and a lower boundary of this second class. Next, we need to find the boundary between class 2 and class 3. So we'll take 90 and 91 and we'll average them, and that'll give me 90.5. So that's the upper boundary for the second class and the lower boundary for the third class. If I were listing all the boundaries, I wouldn't have to list 90.5 twice. You can simply list it once. In this table version, I want you to know that it is a boundary between classes. So it surrounds, so 79.5 and 90.5 surround class 2, which is 80 to 90. So we can go ahead and follow that to fill out the rest of this table in the boundaries column. You can see that I've filled out the rest of the boundaries. So I have the numbers surrounding each class. Except for I don't have the numbers on the lower end of the first class and the upper end of the last class. What you can do there is you can use the idea of our class width of 11 and take the 79.5 and subtract 11 from 79.5. And what will that give you? That will give you 68.5 as your lowest bound. Take your bound of 134.5 and add 11. And what will that give you? That will give you 145.5 as your highest bound. In your homework, you're going to be asked to find the bounds, and you can just list each number once in a list with commas between them. Next, we're going to find the midpoints. So the midpoint of each class, you take the lower limit of that class and the upper limit of that class, add them together, and divide by 2. So first we'll have 69 plus 79 divided by 2. That'll give you 74. Now, you could follow that lower limit plus upper limit divided by 2 pattern the whole way, or you could just note that midpoints are also going to be a class with a part, so we can add 11 to get from one to the next. So if we have 74, 74 plus 11 is 85. And then we'll have 96, 107, 118. And then we'll have 129. And then we'll have 140. Those are your class midpoints. The next thing that we're asked to find is the relative frequencies for each class. So if we were doing a relative frequency distribution all by itself, we would have our class list that our list of classes of circumferences on the left here, and then we could put the relative frequencies right next to it. The first thing we need to know for the relative frequencies is we need to know the total number of items, and we find that by adding up our frequency column. That total is 60. So we'll take each of our frequencies to get our relative frequency. We take each of our frequencies and we'll divide them by 60. So we'll have 2 out of 60, 3 out of 60, 8 out of 60, 19 out of 60, 22 out of 60, 3 out of 60, and then 3 out of 60 again. We can go ahead and put those in our calculator. You can see all of our relative frequencies listed as a decimal. We could also change those to percents by multiplying each by 100. For the last part of this exercise, we're asked to make a cumulative frequency distribution. So I actually split the last column into two, so I could put my classes in a cumulative format, and then I'll have my frequencies listed. So for my first box right here, I want to represent something that is all of the circumferences that come at the first class or lower. So that is all of my circumferences that are less than where my second class begins. So all the circumferences less than 80. For my second box, I'm looking for all the circumferences that would fall into the first or second class. So that's all of the circumferences that come before the second class begins. So that is C is less than 91. And I'll follow that same pattern, and you can even think I'm adding my class width every time. So I'll have C is less than 102. And then add 11. C is less than 113. C is less than 124. C is less than 135. And finally, add 11, which is your class width. C is less than 146. So those are my cumulative classes. And remember, the first frequency box, we're including everything that falls in the first class. So that would be 2. But the second one, we want everything in the first and second class. So I'm going to take that 2 and I'm going to add 3 to it, and I'll get 5. Now I'm going to take that 5 and add the number from the third class, which is 8. 5 plus 8 equals 13. Now I'm going to take that 13 and add the 19 from the fourth class, which will give me 32. Now I'll take that 32 and I will add 22, and I'll get 54. And then I'll take 54 and add 3 from the sixth class. And that gives me 57 for my cumulative frequency. So there are 57 data items less than 135. And finally, I'll add 3 more to that and get 3, and we'll get 60. And there were 60 data items, so I know I have everything accounted for. We've now discussed all of the parts of a frequency distribution and types of a frequency distribution, and we've even made one on our own. One of the great things about a frequency distribution is it kind of helps us figure out the shape of our data. So a normal distribution is bell-shaped. Frequencies start low and then increase to 1 or 2 higher frequencies, then decrease to a slightly low frequency. So we call that normal. And I'm going to draw a picture here of a normal distribution. So it starts low, goes up in the middle, and then tapers down in the same shape. It's symmetrical. That's a normal distribution. And for a normal distribution, I'm mentioning this now, but we'll actually talk about it more next week. The mean is in the middle, and the median is also in the middle. So For normal distribution, that's the shape of it. It's approximately symmetric. The frequencies before the maximum and after the maximum are roughly a mirror image like we have there. But there's also other types of ways we characterize distributions. It could be skewed to the left. Something skewed to the left has a tail on the left side and most of the data is towards the right. So that is a negative skew is what it's called. And when you think about a negative skew, we'd have most of our data sitting in one area, right? So the median or middle value would be up here. But then I think if we're taking tests and most of the class performed in one particular area, but then there's one person that didn't take the test. So our class average for the test takers, we'll say, was like 83%. But then if we factor in that zero is going to bring down the score. So our average would be lower. So in something that's skewed left, you're going to have your mean lower than your median. And this is a little bit extra from this week's objectives. So if the median and mean thing is throwing you off right now, don't worry. We're going to talk about it in more detail in later sections. I'm just adding it in right now. So when you look back and review, you'll have that information there. So just write it down for now. Then we could have skewed right, which is positive skew. In a positive skew, most of the data sits in one area. Then we have a few data items that are up much higher than the rest. So our middle, if I lined all the data up in order, our middle piece of data might sit about right here. Our middle piece of data is called our median. And then pretend that this is a test. In our class on this test, the median value was around 77%. Now, most people did in the area of this median value, but there was one person who aced the test and got 100. That grade is going to bring up our class average. So the average is another word for the mean. So in this case, when you're skewed right, your mean is higher than your median. Once again, this is just a little bit extra as far as mean and median, but we should know that normal shaped is symmetrical with more of the values in the middle. Looking at our tree circumference frequency distribution, let's see if it appears normal. So our frequency distribution here, it starts lower and then it gets higher. The values get higher in the middle and then they taper low again. So we might say that this is roughly normal and it might be skewed a little bit towards the negative end because this isn't quite the middle, but it might be considered roughly normal. More important ideas to consider. First is gaps in data. The presence of gaps can show that the data are from two or more populations. The converse is not true because the data from different populations don't necessarily have gaps. So here we have a frequency distribution of weights of pennies, and you can see that there's a number of pennies in these lower two classes, and then there's a big old gap and for three classes, and then we have a number of pennies in these higher two classes. This might make you say, what's going on? Looking at these, we see a large gap. It suggests we have two different populations, and we actually do. Pennies from before 1983 have 95% copper and 5% zinc. Pennies from after 1983 are 2.5% copper and 79.5% zinc. The last way that we might use frequency distributions is to compare data. You can see here we have Dunkin' Donuts and McDonald's being compared with their wait times for the drive-thru in seconds. By comparing the relative frequencies, we can see that there are major differences. The Dunkin' Donuts service time appears to be lower than those at McDonald's. That may make sense though, because at Dunkin' Donuts, a lot of people are going through just to get a coffee or something that's ready-made, like a donut. Whereas McDonald's, if you're getting a burger and fries, there's a cook time for that. Would it be reasonable to use regular frequency distribution instead of a relative frequency distribution for this comparison? It would not be reasonable because we don't necessarily have the same number of data items for McDonald's drive-thru and for Dunkin's drive-thru. And if we're comparing numbers, but it's not out of the same pool or the same sample size, then it's not going to make any sense. So here a percentage works better.